In this unit, we're going to be talking about solutions. So let's find out some more. So a mixture is a combination of two or more pure substances. Pure substances include elements and molecules. Some examples of mixture include air, water from the tap, hot chocolate, paint, 14-karat gold, stainless steel. Metal mixtures like 14-karat gold and stainless steel we actually call alloys. We can talk about mixtures in terms of being heterogeneous, with hetero meaning different, or homogeneous, with homo meaning the same. We went over this first semester. So a solution is always a homogeneous mixture, meaning that everything looks the same. We can't see the individual parts. So like we just said, solutions are all homogeneous mixtures. So the solute is the substance being dissolved. In our picture example over here, that's the sugar. The solvent is the thing that is doing the dissolving. In our case, in that picture, the water. So if I mix cream into my coffee, what is the solute and which is the solvent? So in our coffee cream example, the cream is the solute, it's the thing that's going to be dissolved, and our coffee is the solvent, the one doing the dissolving. Once the solute is evenly dissolved, what do we call our nice creamy coffee? We call it a homogeneous mixture or a solution. So some characteristics of solutions that you need to know are that they are homogeneous. Already covered that one. The solute will not settle out of the solution, meaning you don't see any of it settle down to the bottom. It cannot be separated just by filtering. The solution has different properties than the solute and the solvent did separately. For example, salt and water have different properties separately than salt water does. The solution is considered to be one physical state of matter, even though the solute and solvent can be in different states of matter. And not all substances can combine to form a solution. So we can't make a solution out of everything. Only certain things can become solutions. So solutions are considered to be in one physical state of matter, but can be made up of any combination of states of matter for their solute and solvents. Can you think of an example for each? So for a liquid and liquid, we have our coffee and cream example that we just talked about. For gas and liquid, a common example you're familiar with is carbon dioxide in water to make soda. For gas and a gas, nitrogen, oxygen, argon, carbon dioxide, water vapor, and small amounts of other gases are in the air you are breathing right now as you watch this video. And the air around you is a solution. You can't see the individual parts. Solid and liquid, salt and water, also known as seawater. And for a solid and a solid, copper and nickel create the nickel coin that you know and love. And remember, all metal solutions are called alloys. So let's talk about solubility. Solubility refers to a solute's ability to be dissolved by the solvent. So whether it can be dissolved or not. A substance is soluble if it's able to be dissolved in a given solvent. Now remember, a solute might be soluble in one solvent, but not in another solvent. A substance is said to be insoluble if it stays in its original state in the solvent, aka it does not dissolve. Liquids that are dissolved in one another are called miscible, and liquids that do not dissolve in one another are called immiscible. So liquids dissolving in liquids get their own special terminology that you need to know. So this brings us to solubility and polarity, something we covered last semester. So as you know, polar means having opposite ends, a positive end and a negative end. Polar substances include ionic compounds, acids, and polar covalent compounds. Nonpolar substances include nonpolar covalent molecules and diatomic molecules. And as you remember, Water is an incredibly polar substance. And when we were learning about polarity last semester, we talked about like dissolves like, and we did a lab on it, where polar substances dissolved other polar substances and nonpolar substances dissolved other nonpolar substances. But polar cannot dissolve nonpolar, and nonpolar cannot dissolve polar. Only like can dissolve like. Water is considered the universal solvent, meaning it can dissolve most solvents, and it's because it's very polar, and most substances are polar. So why do you think oil and water don't mix? Well, oil and other fats are nonpolar, so they don't dissolve in water. Soap is also nonpolar, so that's why it's able to dissolve grease, because like dissolves like, so the grease is nonpolar, the soap is nonpolar, so it can break it down. So what about dissolving? So remember, polar substances like ionic compounds in water are composed of a positive end and a negative end. There are two phases of dissolving. There is solvation, which is the process of attraction and association of molecules of a solvent with molecules or ions in the solute, and dissociation, the separation of solute molecules and spreading of solute through solution with more solvent surrounding. For example, when sodium chloride dissolves in water, sodium chloride separates into sodium ions and chlorine ions in solution. I want you to model this and label the solvation and dissociation. You can pause the video if you need to and come back once you've done your model and labeling. So we can describe solutions in different ways. We can describe them in terms of their concentration, which means the amount of solute in a solvent. A concentrated solution has a relatively high amount of solute in it. So if you've ever heard about juice from concentrate, that means they took something that had a very concentrated amount of juice in it and then watered it down. A dilute solution has a relatively low amount of solute in it. So let's talk a little bit more about saturation. So do you think you could dissolve a whole bag of sugar in a cup of water? You're probably sitting there saying, no, it wouldn't all dissolve. And that's because there is a limit to the amount of solute that can be dissolved in a solution, and we call that the saturation limit. Saturation limits change when temperature and pressure change. For example, the warmer it is, the higher the saturation limit is going to be. You know this. It's easier to dissolve sugar in warm water than it is cold water. We've changed the saturation limit. A solution is saturated if the solution is at its maximum concentration for that given temperature and pressure. You can tell a solution is saturated when you add solute and it won't dissolve anymore. Meanwhile, unsaturated solutions still have room for more solute to dissolve in them. And you can tell a solution is unsaturated when you add more solute and it continues to dissolve. Which brings us to a special kind of solution called a supersaturated solution. And a supersaturated solution actually holds more solute than it's supposed to, more than its saturation limit. So a solution can become supersaturated when it is saturated, and then we heat it to raise that saturation limit. We add more solute, and then you let it cool down very slowly. The thing about this is at a cooler temperature, any slight disturbance will trigger the precipitation of the solid back out of the solution. It's really cool. If you want to look up supersaturated videos online, they look like they're snowing inside like a snow globe. It's super cool, and you should look up some videos of it. You can tell a solution is supersaturated when you add a small amount of solute and a large amount of solute begins to precipitate back out. So as far as solubility curves are concerned, they are a graphical representation of the solubility of substances. And we can put more than one substance on a solubility curve at a time, like you can see in the diagram. So solubility curves show how much a solute can be dissolved in 100 grams or 100 milliliters of water at a given temperature or pressure. So at this solubility one, we can see our temperature is at the bottom. We have grams of solute per 100 grams of water. So if we have 100 grams of water, you can see at what temperature you'll be able to dissolve a maximum of that substance. What happens to solubility at substances as temperature increases? So as we move across our temperature down here, you can see for the most part, they are all able to dissolve more as our temperature increases, with the exception of ammonia here. As we increase the temperature, it no longer is able to do that. And that's because they're gases, and gases actually prefer for it to be cooler in order to dissolve. On a solubility curve, the curves indicate the concentration of a saturated solution, the maximum amount of solute that will dissolve in that specific temperature. So for example, using our sodium chloride right here, we could see that at 70 degrees, we're going to be able to dissolve 40 grams. That's the maximum that's going to be able to dissolve in 100 grams of H2O. Values on the graph below are represented unsaturated solutions. More solute could be added at that temperature. So for example, if at 70 degrees we only added 30 grams of sodium chloride, it would be an unsaturated solution because we could go all the way up to 40. So let's use our solubility curve and answer some questions. So what solute is the most soluble at 10 degrees Celsius? So we go to our 10 degrees Celsius down here, and we're looking for what is going to be able to have the most in there. So what is the highest up? And in our case, that's potassium iodide, Ki, is going to be able to dissolve about 135 grams. What solute is the least soluble at 40 degrees Celsius? So we go to 40, and we have our KClO4 being the least soluble at 40 degrees because it is the lowest on our table. For 3, you are asked how much solute is in a saturated solution of ammonia at 25 degrees Celsius. So we have our ammonia line right here. We go to 25 degrees Celsius and bring it up, and we're at about the 55 grams of ammonia can be in 100 grams of water mark. If potassium nitrate has 70 grams of solute dissolved at 60 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? So we need to find our potassium nitrate, which is this line right here. And we're going to go to 60 degrees and 70, which is this right here. So it falls below the line, meaning it is an unsaturated solution. If a solution of sodium chloride, that's this line right here, has 20 grams dissolved at 90 degrees Celsius, is it saturated, unsaturated, or supersaturated? So we go to 90, we go up to 20. It is also unsaturated because it falls below the line. So let's talk about the rate of dissolution. The rate of dissolution is how quickly something dissolves. If you are making sweet tea and you are trying to dissolve a lot of sugar, how can you make the process of dissolving sugar go faster? Well, three factors are going to affect the rate of dissolving to help you in your sweet tea making, and that's surface area, agitation, and temperature. So surface area is the dissolving process occurs at the surface of whatever solid is being dissolved. Only the very surface is being acted on, not the stuff inside yet. The more surface is exposed, the quicker the dissolving is. So which would be faster, a cube of sugar or crushed sugar? Well, it's going to be crushed sugar because it has a lot more surface area. Our second factor was agitation. And agitation, such as stirring, shaking, or mixing, removes newly dissolved particles from the solid surface and continually exposes that surface to fresh solvent, which is why stirring speeds things up. And our last one is temperature. The higher temperature causes the solvent to move more quickly, thus increasing the rate of dissolving for solids, but decreasing the dissolving rate of gases. Solubility of gases decrease when the temperature increases because the molecules move too fast and they escape rather than dissolve. And this is shown in a solubility curve by having a downward sloping curve instead of an upward sloping curve. All right, that was quite the intro to solutions. Can't wait to teach you more.